So, this is a road where I have certain traffic, a certain flow, and maybe I have a speed breaker here. So, there are different vehicles so they travel to the right. When they come on the speed breaker, their speed reduces and then they again go further downstream. And in fact, what could happen is that I could sit here as an Eulerian observer and I would see maybe the vehicles are going at 60 kilometers per hour. And I again see the vehicles here are 60 kilometers per hour, but at the speed breaker they are 10 kilometers per hour. And all vehicles do that. So, a vehicle comes, slows down and then speeds up again. But if I position myself at any location, then at each and every location the speed is not changing with time. Okay? So, what is happening is that if I am a Lagrangian observer, I follow, let us say, this particular vehicle, then its speed reduces and then increases again. But if I station myself as an Eulerian observer, then of course things are not changing with time, they are constant. So, that is what is being said here. And why is this happening? It is simply because of the equations here. So, again if I interpret, let us say, just the first equation, the acceleration of a certain vehicle, the material rate of change of speed, then we are saying because it is a steady flow, so this quantity is 0, it is not changing. But these quantities could still change because my things are changing with x. So, if I put my x coordinate system along the road, then actually I am talking about dvx by dt is del vx by del t. This is 0 for steady flow, and plus I have Vx del Vx by del x. Notice I have gotten rid of these two terms because I am talking about some kind of a one dimension only. Of course, x is curved. So, a material acceleration could still take place because there is a change in Vx along x. Okay? If Vx was uniform, so suppose there was no speed breaker and my vehicles were everywhere going with 60 kilometers per hour, then the material acceleration would also be 0. Okay? So, I hope you are able to understand what constitutes a steady state. So, steady state implies that this Eulerian or the local derivative is 0 everywhere. The material derivative could still be non-zero. All right. You may also want to note that steady versus unsteady is frame dependent. So, I could have a frame of reference in which the flow appears steady and the same flow in another frame of reference would actually appear to be unsteady. Let me give you an example. So, the example that I want to give you about frame dependence is of a boat. So, imagine there is a boat and this boat is moving to the left, and of course this is some kind of a river, okay, and this has a certain wake. Suppose I am an observer who is sitting here. If I am an observer on the shore, then what I see is that the boat moves from the right to the left, and if I record the speed or the pressure or any quantity, let us say at this point, suppose I call this as point A, then I would see that speed changes with time. Okay. So, when the boat is far away, then the river is still, so I do not record any speed, or maybe it is a lake, and when the boat approaches me, then the speed here starts increasing, and then finally when the boat has gone away, again my speed goes to 0. Okay. So, see, observer on the shore actually sees an unsteady flow. Same boat, but now I have an observer who is sitting here, and what this observer sees, so this is an observer on the boat. I mean, I could have another observer who is on a different boat and is traveling with the same speed, or I could have an observer who is on a helicopter and who is following this boat. So, we are not talking about the observer being actually on the boat, but the point is the observer is moving with the speed of the boat. And what that observer sees is that actually the boat is stationary. Okay. So, boat is stationary. And in fact, the inflow is steady. So, there is a flow that comes onto the boat, and this observer, suppose he, from his point of view, he looks at a point A which is attached to his frame of reference. So, the coordinate of this point is fixed because it is moving with the boat. So, he sees that nothing changes here. So, this would lead to a steady flow. Okay. So, it is the same phenomena, and one person who examines it from a certain stationary frame at the shore thinks that the flow is unsteady, but you do a small change of frame of reference and you get a steady flow. So, in fluid mechanics it is extremely important to choose the correct frame of reference. A flow which could be very complex in one frame could become a little bit simple in another frame. Okay. The same is true for many other situations, and I encourage you to think of them, what happens for a change of frame of reference. Okay, now I want to talk about the description of the flow. So, we will not talk about the graphical description of flow. Okay. So, there are certain fluid elements which are moving and I want to track them. Okay. So, the first thing I want to talk about is a path line. So, this is essentially just a trajectory of a fluid element. So, you know, again, if I consider the blackboard as some kind of a two-dimensional plane in which there is a fluid flow, and there are some I just follow a fluid particle, then the trajectory of it is known as a path line. You can see that this is actually very similar to a Lagrangian description. But as I said, this would not be so useful as far as fluid mechanics is concerned, because we are more interested in a Eulerian description. How can I get path lines? I can use tracer particles that go with flow without disturbing it. So if I have a certain flow, I could inject some particles and then they are carried with the fluid elements and I can track them with a camera or some such thing and I would be able to see what a path line is. This is extremely useful. Then I can understand a little bit about the behavior of the flow. Another possibility is many people use what are called hydrogen bubbles. So they will use bursts of hydrogen bubbles from an electrode. So what could happen is I have a flow on this plane and I put in an electrode and then I pass current for a short time. So some hydrogen bubbles are created and they are carried with the fluid. Okay, so if I can track the hydrogen bubbles as they move along, I would be able to see what is happening to my flow. For example, I can measure the speed of the bubbles and so on and so forth, their relative movements to each other and so on. So that's path line, very, very intuitive. Okay. The next thing I want to talk to you about is a streamline. So streamline is another interesting concept where tangents to streamline give us the local velocity direction at each point. Okay, so this is instantaneous. Okay, so suppose this is my streamline, and then if I took a point here, then the tangent to this point would be in the direction of the velocity. Okay, so very simple. This of course is an Eulerian concept. Okay, so it's instantaneous. I take a picture of the flow and then I construct these concepts out of it. So what is the description of a streamline? So suppose I take an infinitesimal part of the streamline and let's say that I represent by dr. So the equation of a streamline is that dr cross v should be 0, simply because dr is tangential to v. Okay, so their cross product has to be 0. So I could then expand this and say this is I, j, k, this is dx, dy, dz, vx, vy, vz, and this is 0. Right? It's a vector equation. And from this I would be able to see that I get 3 equations. So the first equation gives me that dy vz is equal to vy. The second equation would be vz dx is equal to vx dz. And then I can get the jth equation, which is the kth equation, which is V y dx is equal to Vx dy. So this is actually the equation of streamline. Okay. So if I integrate these three equations, I would be able to get the line in 3 dimensions. What about in 2D? So in 2D, I could simply take this equation over here, and I would see that dy by dx is simply given as Vy by Vx. Okay, that's the equation of a streamline. That means the slope of this line is of course related to the slope of the velocity vector. This is in 2 dimensions, and I could get actually all these lines in 3 dimensions. So it's a very interesting concept, and you can see that by definition no flow can cross a streamline. So I am going to write that here, that flow cannot cross a streamline. Okay. In fact, a corollary of this is that if I draw two streamlines, so this is streamline 1 and this here is streamline 2, the flow cannot cross these two streamlines, so it has to stay in between. So therefore, this combination gives me what is called as a stream tube, and the volume flow rate is preserved. So whatever flow enters this, let us say the volume flow rate is Q, that has to flow throughout the stream tube because it just cannot leave the stream tube. So it's a very interesting concept. Alright, so I have talked to you about a path line and I have talked to you about a streamline. There is another very interesting concept which is called the streak line. So suppose we inject tracer particles at some location in the flow. Okay. Then the trajectory, or rather the locus of all points, rather the tracer points at a certain instant that's what gives me a streak line. Okay. So essentially what we are saying is that either I could be injecting tracer particles and they go at different locations in the flow. I take a picture and wherever those particles are at that point, the locus of all those points would give me a streak line. That is one way of looking at it. The other way is that all the particles that have passed through a certain location in the flow, okay, their present location, the locus of that would give me a streak line. So an example would be the smoke from a chimney. So this is a chimney and there is smoke coming out of it. So there is a point P here, and you can imagine all the smoke at some point would, at some time instant, would cross this point P. And therefore, if I get this trajectory, this is a streak line. Because this particle here passed through the point P long time ago. This particle here had crossed this point at some time, and so on and so forth. Okay? So that would be a streak line. So we have now three concepts: streamline, path line, and streak lines. Okay? And how are they related? I would like to explain this to you through an example. So let's consider an example. Let's consider a velocity field in 2D such that for t less than equal to 5 seconds, I have flow only along the x direction. So this is 1 meter per second in the I plus 0 j. So I have just velocity along the x direction everywhere. And then for t greater than 5 seconds, let's say I still have the magnitude as 1, but now it is at an angle 45 degrees. So I would say cos 45 degree I plus sine 45 degrees j. Okay, so essentially the flow is suddenly turning directions. So till 5 seconds it was in the x direction, and then after 5 seconds it actually goes at a 45 degree to the x axis. And I would now like to see what happens to the path lines, what happens to the streamlines, and what happens to the streak lines. So let me draw them for you. Show you the streamlines. As you know, streamlines are instantaneous lines. Okay, so I would have to now consider t less than 5 seconds and t greater than 5 seconds. So let me do that. So this is t less than equal to 5 seconds, and here I am going to plot t greater than 5 seconds. So these streamlines are simply these lines over here. Okay? Because tangents to these give me the direction of the velocity, as simple as that. For greater than 5 seconds, I would have to draw these lines at 45 degree angles. So these are my streamlines for a larger time, and any time greater than 5 seconds, this is how it looks like. So you can see the streamlines go through an abrupt change at t equal to 5 seconds, they suddenly change direction. Is this an unsteady flow? The answer is yes, because the flow is changing with time. So it is steady up to 5 seconds, it is steady beyond 5 seconds, but then in between it is changing, the velocity is changing with time, of course in a very short span of time, and therefore the flow is unsteady. Okay, what about the streak lines and path lines? So I first want to draw path lines. And then I am going to show you the streak lines. So let us say I want to release the points at this origin 0, and I would like to track the path of particles till 10 seconds. So I am interested in path lines up to 10 seconds of fluid elements that are released in intervals of 1 second at O, the origin, this point. Alright, so the first particle is released at t equal to 0, okay, and I want to understand what is the trajectory of that particle. So clearly it is going to start with a speed of 1 meter per second. So after 1 second it is going to reach a distance of 1 meter, it is going to reach another 1 meter, 3, 4 and 5. Okay, so this is roughly 5 meters it has reached in 5 seconds. And then at 5 seconds suddenly the flow direction changes, and now this guy is going to go like this. Okay, so this is what it travels in 6 seconds, and over here in 7, over here in 8, 9 and 10. So this is where the particle reaches after 10 seconds. Okay. So this I am going to call as the particle at p, which is released at t equal to 0. Let me now trace the particle which is released at 1 second. Okay. So let me start from this point. So the particle which is released at 1 second, so t equal to 1 second. So that particle goes up to here, 2, 3, 4, and now because the velocity changes at t equal to 5 seconds, okay, this particle is now going to go something like this. So this I am going to call the particle which was released at t equal to 1 second. Okay, so you can see that it had less time to go with the velocity field specified in the first interval, but it gets a full 5 seconds to go with this velocity. Similarly, I can talk about the velocity of a particle. So this is p2, and then I could draw here p3, this is p4, and the particle which is released at 5 seconds, okay, it actually does not have any occasion to travel with this speed, it straight away travels with a speed here. So this is particle 5, and they all reach the same height as particle 0. Now the interesting part is what happens to the particle which is released at 6 seconds. So the particle which is released at 6 seconds actually starts from here and reaches only up to here. So this is p6. So this is the trajectory of p6. Okay, and you will notice this is the trajectory of the particle p7, and likewise I could draw p8 and p9. So this is p9, and maybe this one over here is p8. So what I have shown you are the path lines. Okay, so these are the streamlines for t less than 5 and t greater than 5 seconds, and these are path lines of the particles that start from origin. I could draw path lines of other particles also which are not necessarily from origin, and of course they would be different. Now the question is, what about the streak line? So suppose I want streak line at 10 seconds. So I want to get a locus of all those points which started from a certain point O, and they are located somewhere at t equal to 10 seconds. And of course I know that there is a point located right here. So this is just been released at 10 seconds, then this is the point, this is the point. So if I had to draw the streak line, okay, this is the streak line. So this is the streak line, at 10 seconds. Okay. So, this is your streamline. I have already drawn the path lines. Okay. So, this was the path line for the particle which was released at t equal to 0, t equal to 1, 2, 3, 4, 5 and so on, and this is the streak line at 10 seconds. Now, you go back and say, no, I want to find out what is the streak line at t equal to 9 seconds. You can certainly do that. So, at 9 seconds, this particle would have been here, this was here, this one was here, this one was here, this one was here, this one was here, and you would get actually this. This is your streak line at 9 seconds, and so on and so forth. So, I hope you are able to make out that even for this simple example where the velocity field is changing with time, the streamlines, the path lines and the streak lines are different. Okay. Now, streak lines are little bit easier to get in experiments. Okay. So, streak lines are more common in experiments. And therefore, it is important to understand them to make sense out of them. There is one scenario where everything becomes very simple, and that is for a steady flow. For a steady flow, that means a flow that does not change with time in a certain frame of reference, your streamlines path lines and streak lines are identical. So, if you had a steady flow, then all three are exactly the same. So, that is a very special case. But if you had an unsteady flow, then as I showed you, they are different. All right, so we are going to stop here today, and in the next class we are going to talk about the deformation rate of a certain fluid element and then apply the Newtonian law of viscosity to that. Thank you very much.